So we're going to talk about Newton's third law. First, let's just review the first two laws. Newton's first law says an object with no forces acting on it, if it is at rest, it will remain at rest, and if it is in motion, it will remain in motion. And this really means that a force is required to change motion. So something can be moving just fine without a force acting on it, or a net force anyway. But if we want to change that motion in any way, slow it down, bring it to a stop, what have you, change its direction, it requires a force. Then Newton's second law of motion says an object subject to multiple forces will undergo an acceleration. So that's where we get this equation where the net force is equal to the mass times the acceleration. And this net force is also equal to the sum of the forces acting. Now, for Newton's third law. Newton's third law says every force occurs as one member of an action-reaction pair of forces. The two members of an action-reaction pair act on two different objects, and the two members of an action-reaction pair point in opposite directions and are equal in magnitude. So we have an example here in the corner. 1 second. Here you go. Of a hammer and a nail. So the hammer is used to nail into the wall, and it is exerting a force on the nail, but the nail is also exerting a force right back on the hammer. And so we have the hammer and nail bigger, and then another example too. So again, just this part again. So the nail supplies a force on the hammer when the hammer supplies a force on the nail. And this is an action-reaction pair of forces. And the important things here are they're acting on two different objects. So you can't have an action-reaction pair on the same object. That doesn't work. And they are equal in magnitude. The arrows are the same size, but they're opposite in direction. They point in opposite directions. So we can also have this with two blocks being pushed in one direction or another. You don't have that information in here, but what we do have is that block B supplies a force on block A, and block A supplies a force on block B. And it's equal in magnitude, opposite in direction. And that makes it an action-reaction pair of forces. And again, acting on two separate objects. Action-reaction pairs do not act on the same object. So now an example, or, well, I guess a lecture question, really. A 10,000 kilogram truck has a head-on collision with a 1,000 kilogram compact car. During the collision, the force of the truck on the car is greater than the force of the car on the truck. That's choice A. Choice B, the force of the truck on the car is less than the force of the car on the truck, or those forces are equal. So you can pause and think of this, but also this is an example of Newton's third law. This is an action-reaction pair. The two objects should have equal and opposite forces acting on each other. So the answer to this is C. But when you think of a situation like this, I imagine you might intuitively think that the car would react more than the truck. So shouldn't it be experiencing more force? But we can do some math here and see what's actually happening. So this is just Newton's second law, but we're solving for acceleration instead of the net force. So we'll put the acceleration of the car over the acceleration of the truck. So the net force is the same in both cases, but the masses are different. So the net forces cancel out, leaving us with the mass of the truck over the mass of the car. And the truck is 10,000 kilograms, while the car is 1,000 kilograms. So the acceleration of the car is 10 times the acceleration of the truck. So what you actually see, or what your intuition is actually telling you when you are looking at a situation and saying, well, the car is going to react more, or whatever object you're thinking of, that reaction is the acceleration, not the force. The force is the same, but the acceleration is different because the masses are different. So if two objects have the same mass, you might think, okay, those will interact the same amount, react the same amount. And that's because also their accelerations will be the same, because that force that's acting on them is the same. So those are kind of our rules about Newton's third law. They act, and Newton's third law pairs, or action-reaction pairs, act on two different objects. You can't have action-reaction pairs on the same object. They are the same size, but they act in opposite directions. And then, kind of as an aside, the reaction you think of with, differently sized objects supplying forces to each other, that difference you feel is like intuitively is there is the acceleration, not the forces. The forces are the same. Like if a child pushes on an adult's hands and the adult pushes back, the child's going to move more, but the force between their hands is still the same. The child is just less massive, so they accelerate more than the adult does. Okay. We'll keep working on this concept, but I did want to lay it out here first. So then we're just going to do an example. So we have a 5 kilogram block A being pushed with a 3 Newton force. In front of it is a block that is 10 kilograms, block B. The two blocks move together. What is the acceleration of the blocks, and what force does block A exert on block B? So let's work on this. Okay. So to start out, we just want to draw the free body diagrams. Okay, so we'll start with block A. And this is gonna have weight. So weight of block A. Gonna have normal force, so normal force of block A. It has this pushing force from the hand. We'll just call that F push. And then it is in contact with block B, so it is experiencing a force from block B. So force from B on A. Those, oh, and then our net force is going to be going to the right. And then block B. And again, we have a weight force. This one's bigger because block B is, well, maybe I should do it twice as big actually, because it's twice as massive. So weight B, normal B should also be bigger because it's not accelerating through the floor. Normal B. And then the only horizontal force that block B is feeling is the one from block A. So we're going to try and make that the same size, but it's opposite in direction. And this is the force from block A on B. And these, I'm just going to label our action-reaction pair. So here they are. Those are our action-reaction pair of forces. And if we wanted to also see, for example, like the free body diagram for the hand, we could also have the pushing force as an action-reaction pair. But we don't care about the hand in this case. So this is our only action-reaction pair within what we're paying attention to. So now let's write our equations, our force equations. So the net force in y for A. There's no acceleration in y for either of these, but actually I should put that the net force in B is also in that direction to the right. Yep. So in y, our forces for A are the normal force minus the weight force. And then in X, A, this time we have a net force in X. So we'll say mass of A times the acceleration. These blocks are in contact with each other, and there's no mention of them sliding or anything that indicates that they are accelerating at different speeds. So we can assume their accelerations are the same. So I'm just going to use A, but we could write it like this. So the acceleration of A equals the acceleration of B equals just total acceleration for this. And then our forces. So the pushing force is to the right, so that's positive. And then the force from B on A is to the left, so we'll subtract that. And I'm just going to write it BA for that. Now we do the same thing for block B. So this also equals 0 in Y. And then it's the same where it's the normal force minus the weight. And then F net X of B. This time we have mass, or well, we always had mass, but we have acceleration. So we have the MA term. And then the only force, the only horizontal force on block B is this block or force from A on B, and I'll just write it AB again. So these forces here are our action-reaction pair of forces. So these are the same. So for example, let's take a closer look at these equations. MA times acceleration equals the pushing force, not the forcing, push. FBA, and then we have mass B times A equals FAB. So like I said, FBA and FAB are the same magnitude. The direction is already accounted for in writing our force equation. So we don't have to worry about that part. So we can just substitute, we can plug in this here because we want to solve for the acceleration. So we can plug that into our other equation because, well, I guess let's first look at this equation. Do our due diligence. We know the mass, we want the acceleration, we know the pushing force, and we don't know what this force is. And again, we know the mass, we don't know this or this, but we have two equations. This requires, like, we can solve something with two unknowns if we have two equations, but it requires both of them. So that's what we're going to do. We're going to substitute in mass times acceleration, mass B times acceleration for this here, and then solve for acceleration. So let's see. A times acceleration equals the pushing force minus MB times acceleration. And I'm going to add mass B times acceleration to both sides because we're solving for acceleration, so we want to get it on one side of the equation. So MAA plus MBA equals the pushing force. And then I'm just gonna factor the acceleration out there. So what that looks like is just MA plus MB times the acceleration equals the pushing force. Cool. And then we will just divide, oh, no, not erase. Divide mass A and mass B from both sides, so we get that acceleration by itself. And that looks like A is equal to the pushing force divided by mass A plus mass B. And these are, so the pushing force is 3 newtons. Mass A is 5 kilograms and mass B is 10 kilograms. And this gives us an acceleration of 0.2 meters per second squared. So we got that first part, we got the acceleration. Now we want to find the force that block A exerts on block B, which is this force here. And would you look at that? We have an equation and we now know what the acceleration is, so we can just plug stuff in. So force from A on B equals the mass of B times the acceleration. So mass of B is 10 kilograms, acceleration is 0.2 meters per second squared. That tells us that the force is 2 newtons. So let's just go back over what we did really quick. So we drew our free body diagram. And we labeled our action-reaction pair of forces, which is the force between the two blocks, or that each block exerts on the other. And then we wrote our force equations, and we also we labeled our action-reaction pairs again. Then we took a closer look at the relevant equations because the y direction equations aren't really going to give us anything here. And we used our technique of, okay, what do we know? What don't we know? And we saw that in both equations, we had 2 things we didn't know. But it was the same 2 things in each equation. So when you have 2 unknowns and 2 equations, you can solve them. So if the number of things you don't know matches the number of equations you have, then you can solve for it. And so that's what we did. We just plugged in mass B times acceleration into the A equation and solved for acceleration. We got 0.2 meters per second squared. And then we would just plug that back in to the B equation and solved for the force of A on B, which is what it asked for. Okay. So that is the process of solving, or really using action-reaction pairs of forces to solve situations. We're going to do more of this in class on Tuesday. And you have some at least thinking to do about it for your assignment today. So you're welcome for the shorter than usual lecture, because I mainly just want you to spend some time with this concept. Yeah, have a great day.